Hello there, and welcome to my video report for Lab 1 on constant velocity. I would just like to start off by talking about what is constant velocity, and the way I think about it is like this. I see constant velocity represented as when an object is moving over a period of time where it is neither speeding up or slowing down. So if we talk about another quantity, for example acceleration, which is equal to the rate of change of velocity, we can see that when we link this to constant velocity, the acceleration is going to be equal to 0 because the velocity is not changing over a period of time. So then if we go back further and look at Newton's second law, where F equals ma, we can deduce from this that the net force is going to be equal to 0 as well. So I'd like to start off today by showing you the video that I created, and I'm going to do this now by opening Tracker. So here we can see I've opened Tracker, I've got my video ready up and to go, and I'm just going to move the ball back to the start quickly. Right, so what we can see here is basically my kitchen floor, and the object I've chosen to use is a football, as I thought it was probably the most simplest thing to use. Now as you can see, we've got the first little red circle there, that's to represent the point mass of the object. I've done my best to keep it in the centre for each frames, however it's not going to be perfect. On the right hand side we can see we've got the plot of the graph of the objects where it's going, and also where we've got the table of the times when for each frame and the position, how far it is away from the origin. So I'm just going to click on the axes, and you can see I've set them so in the first frame I'm taking a ball to start from the origin, and then we can just see here the calibration stick. I've got that in, I've measured that up in another frame, and I've set the length to be 0.22, the diameter of the football. So I'm just going to play the video through now. As we can see, it's not the best quality, I haven't got the best camera, but I think it was good enough for the experiment, as I was roughly able to find the centre of mass. But as we can see over on the plot, towards the middle of the graph we can see it's not like following the trend, it's just gone off a bit. But if we look towards the start and the end, it is a bit straight, but it's not brilliant. So I'm just going to close that down now and open up VIdle, VPython, where I've got the program set up. And basically at the top I haven't really altered anything, I've kept that the same. So I'm just moving down now to system properties and the initial conditions. We can see I've put the mass of the ball in to be 0.45 kilograms. Now the initial conditions, basically the ball's initial position and velocity I'm taking for when t equals 0. As we can see, when t equals 0, x is equal to minus 0.008. So that's why the ball's initial position is minus 0.008 for the on the x-axis. And if we go back, I worked out the initial velocity by taking the two first values in the table for both the time and the position, and I've worked them out in the way that would give me the initial velocity, which comes out as minus 0.68. Now looking at the time step, I've taken delta t to be 0.01. We can take 100 readings in a second there, and if we just go back to Tracker for a second, we can see that it lasted for 1.33 seconds. So we're going to take around 133 readings when doing the experiment for the model. Right, so now moving along down, we're going to look at basically what it's going to be carried out during the loop. As we can see, well, I've started off by saying while t is less than 1.333, that's basically how long it took for me to do my experiment, so that's how long I would like this to elapse for. As we can see, starting off, we've noticed that we put fnet equals a 0 vector, which is what we want because we're dealing with constant velocity, and we know that the resultant force is going to be 0. And we just see we've got the equations in there for working out the new velocity and position for each corresponding velocity and position we've been dealing with. I'm just going to go ahead now and run the program to see what we get. There we go, it's just popped up now. So on the bottom one we have the graph where we've got time on the x-axis, position on the y-axis, and as you can see perfectly straight lines being done. Then in the top left hand window I've got the ball which is represented by that blue sphere, and the origin represented by the yellow sphere, and the path represented by the green line. So we're just going to close them down now. We've got two sets of data, both for the experiment which I carried out using Tracker, and VIDLE, VPython, the model. So now what I'm going to do is going to open up a spreadsheet and put all this information into some tables. As you can see here, on the left hand side we've got time. The second column I've got the experimental position, and then on the last column on the right I've got the position for the model. As we can see, the first couple of values for the time, there's around 20 of them. That's the times that I've taken in my experiment, and then corresponding to them is the positions that's been coming out. If we scroll a bit further down, we can see that we've got the times there for the actual model being carried out, and we can see we've got much more there because I'm using this much smaller time steps, so the result's going to be more reliable. So we go and look at the graph now. Just click on that now and open it. What we're going to come out to see is what I expected to see when we ran the model, and it's come out for the model exactly what we saw when we run the program. We've got a perfectly straight line, and if we look at the axes again, we can see on the x-axis we've got time, and on the y-axis we've got position. So looking back to this line, it looked really similar to what we see when we ran the program in VIDLE. It's straight, and if we would work out the velocity between time 0 and 0.3, and then take the corresponding values for time and position, the velocity there would be the same, for example, if we wanted to take the velocity between the time 1.2, for example, and 0, and then corresponding value. The velocity would be same for each and every section we'd like to take it for, because the velocity is constant throughout. Now, looking at my results quickly, we can see it's not as many blue spheres, as because I didn't take as many readings. I only took 20, whereas in the model it took 133 roughly. It started off well, but towards the end you can see that completely gone off. It's quite far away from the model's position results. So we can see at 1.2 seconds my football in experiment's gone around 1 metre in the negative x direction, whereas in the model it only went around minus 0.8. So we can see it's a bit off. The only thing I can suggest about that is maybe it was accelerating. There might have been a net force on it, and it wasn't travelling at constant velocity, which is something that I could improve on. So thank you for watching my video. I hope you enjoyed it. I hope you've also learnt something from it as well, and I look forward to hearing the feedback from you. Thank you very much. Bye bye.